and direction. So example of a scalar quantity is our area, our volume, our mass, our time. These things have magnitude, like they have some specific amount of weight or should I say quantity that are portioned to it, but they don't have a specific direction in which they are working. So if you say if you are declaring the time either in milliseconds or in seconds or a minute or an hour or by any particular unit whatsoever, it has some particular quantity that is associated with it. But you cannot say that, oh, this time is working in so direction, this time is working in so direction. It's not like that. But when it comes to vector quantities, there are quantities that have both magnitude and direction, which means the same way they have the weight that they hold, they also have the direction in which they operate. If you are looking at force, you can see force as a
Eh?
particular entity which it has its own
Eh?
relating. And say, okay, oh, the force of probably
Keyboard
we
is
have
full.
3 Newton that's exerted on an object
Okay,
in a
give me
particular direction. Yeah, that's
send
force.
this.
When
Send
you are
this.
looking at your velocity and your acceleration, you are looking at the rate of change of speed with time, and also for a particular body moving in a particular direction. Geometric representation of vectors in 1 to 3 dimensions. So we are looking at our 1D, our 2D, and our 3D. So when you have vector quantity can be represented graphically by lines drawn so that the length of the line will denote the magnitude according to the stated vector scale, while the direction of the line represents the direction in which the vector quantity acts. This is telling you that whenever we are drawing a vector graphically, like we are penning down the structure of a vector, we will have line that will indicate um, the what's it called, the magnitude and the direction. So in a more practical sense, what that place is trying to tell us is that just this guy's doing it.
No. You've actually muted your device. Please check it. You've actually muted it. Let's just wait for him. Let's wait for him while he joined us. Please, I will just encourage us as we are joining the session. Kindly introduce your name, your name, your study center, and your level, and even necessary your department, because NACOS is split. We have several departments on NACOS. We have the computer science department, we have the information technology department, and we have computer science mathematics department. So kindly indicate the one you are from so we can know our people. So thank you very much. So let's just wait for him. I believe it will join us. We are only seeing his screen. Okay.
Hello.
Yeah, we can hear you. We can hear you.
All right, I was trying to share my screen from my mobile while I was trying to draw a vector the other time, and all of a sudden I lost connection.
Okay. Mastercraft, we can't hear you. I think uh, I think he's actually having a problem. So the network issue now. We know Nigeria now. We sabi how it take look like. So please let's just mute our device. As I said earlier, I think I only saw two people that are introducing themselves. Avegeni Jenny. I'm still expecting you to throw down your name.
Guys, please apologies for the break in transmission. Yeah, I believe everybody should be hearing me now. Um,
Yeah, we can hear you.
all right. So from where I stopped, I was trying to like explain the geometric representation of vectors and what they mean by when they say vectors are when they are graphically drawn in terms of their magnitude and direction. So let's say you have a vector AB, that's a vector that goes from A to B, and it's just like a line that is drawn, such as this. The direction is denoted with the arrow that is on the point of your vector. So while the magnitude is denoted by what's it called, the length of the line that is drawn. So let's say from length here, let's say from this length to this length is just going to give us um I'm going to call that something that evaluates to probably 5 Newton. So you call that, apologies for that. We are going to call that our 5n. In a rough what's it called, rough explanation, the direction in which it faces is denoted by the arrows, while the length of the line that is drawn denotes the magnitude. So like I said earlier, our representation can actually be in a one dimension, two dimension, three dimension. So when we have something on a straight line that is just a single line like this, that what I've drawn earlier, that's just a one dimension there. What's it called? If you have something better like
Aṣọ lọ sọ́dọ̀
the,
girama lọ gba pure water tó mú ní wọ́n máa wà lọ́wọ́.
you have something better like something
Sọ
like
mo fẹ́ gba pure water tó wà
this.
lọ́wọ́ ẹ̀.
So this one is
Ó yá
going
come
to is
close ẹ̀.
just a two-dimensional what's it called? A two-dimensional vector representation, because we have the line drawn on the x and y axis. So what you have here is going to be our y, and what we have here is going to be our x. But paraventure is a 3D vector representation in which you have three different vector units. Then you are going to have the third dimension, and most of the time the third dimension is sometimes drawn as something that extrudes, like from here down here, like from this junction here down here, and they call it the z axis. The z-axis. So that's the origin of x, y, and z axis for our three dimension. While for the one dimension, we only have either y axis alone or x axis alone. So that's that about the geometric representation of vectors. So when we talk about two equal vectors, vectors are said to be equal if they have the same magnitude and direction. So that means if you have two different vectors and they are moving in the same direction, and also they are of the same length, so you can see that, okay, oh, these two vectors are equal. And there are some couple of types of vectors that are listed out here. We have the position vector, we have the line vector, and the true vector. So when we say position, the difference between position, line, and fixed is for you to know that position is fixed, and line, even though it can probably move, like it's not as fixed as a position vector. But a line vector is actually dependent on the action of an external resultant force that is acting on it. So uh, okay, let me quickly clean this page up. All right, just imagine that you have a vector representation of something that looks like this. You have a vector representation of something that looks like this. You can practically have a resultant a resultant force acting on it that can probably make it shift its position. Hold on. That can make it shift its position, and for you to have something like this. So this particular third line, we call it our R. So is the resultant vector. You actually find the what is it called? The resultant of a vector with is also said to be the magnitude, and so you can find it with the Pythagoras. So the thing here is, for a particular line vector, the mechanical force acting on it can make it shift its position at that particular point in time. So even though it might appear as if it is fixed, it is not directly fixed. Neither is it entirely free. So the line vector actually like can be represented, or can just be like use the Newton's first law of motion to just understand and remember what the line vector entails. The Newton's first law of motion made us to understand that a particular object will continue to remain in its present state, either at rest or in motion, until an external resultant force is act on that particular body. So the same is true for a line vector. So that line vector will actually maintain its present state unless a mechanical force acts on it, which means it's capable of shifting or sliding along a particular line of action, but it will not shift or slide unless that mechanical force acts on it. Then we have our free vector, which is one that is not restricted in any ways. Now, looking at addition of vectors, we have the sum of two vectors, which is it's indirectly relates to equal vector, where we said two vectors are said to be equal if they have the same magnitude and direction. But when we are adding two vectors together, just take it's just like you are doing your normal addition and subtraction. It is expected that if you have a vector a to b and a vector b to c, if you are adding a to b together, it will give you a to c. So they can probably give you some couple of words, like, okay, if you have something like a plus b, b plus c, c plus d, d plus e. It's just for you to know that, okay, let me kind of do a pictorial representation. So let's say you have AB plus BC plus CD. If you have AB plus CD plus CD plus AB plus BC plus CD, the sum of this one is going to give you AD. It's just for you to know that, okay, whenever you are connecting your vectors together, you have vector A and they are like of close points. So you have your AB to your BC to your CD and back to your AD. So this is like a vector of close point, and whenever you are adding it together, that means you are closing it all up. And adding it together means that your starting point, here, because this place is going to be A, this place is going to be B, while this place gives us C, and this place gives us D. So the way it moves, this one comes here, this one comes here, this one comes here, and this one goes back up here like this. So the way these vectors are adding up, each unit are like joining together to form up a closed vector, is such that whatever your starting point is going to tally with what your end point here is. So your A to B plus B to C plus C to D is going to give you A to D. But then in the addition and summing up of vectors, there's something that you should note. What we did there is just addition, like you just have everything plus 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 plus. So what if you are now doing something like minus? Like they probably give you something that, okay, subtract these things to subtract this thing and give us the answer. It is very, very possible. You can have something like that looks like Okay, let's do um BC. Let's do BC minus DC plus DE, then plus FE. Okay, now let me do minus EF. Yeah, minus EF is equal to what? So now when you look at this one, we have minus here, we have minus here, we also have another minus here. Now when you are looking at minus, when you are subtracting a vector, you tend to like swap the points. You know, this one is B to C, while this one is D to C. So when you have minus here, you swap it to change it to positive. So you are going to rewrite this thing as B to C, B to C plus C to D plus D to E, then plus again, this is F to E. Oh, this one should be F to E, not E to F. Sorry, this one should be F to E. So you have E to F. So the sum of this one is going to give us B to F. The sum is going to be B F. So that's the sum of all this one. So the difference between having a negative operation in your vector, in the sum of a particular vector, is that you just alternate the symbols. Now instead of us having our DC inside here, I alternate it to CD for me to change this negative to positive. So that's that about the brief sum of uh, addition of vectors. Then also the magnitude of the vector sum can be solved using the Pythagoras theorem, which is our hypotenuse raised to power 2 is going to be opposite raised to power 2 plus adjacent raised to power 2. We are going to see this a lot. We are going to see this a lot. But I can give you assurance that one way or the other, there's going to be a question or more than one question set that is going to relate to this particular formula in the whole in your exam, and even in dealing with this course in general. So you have your resultant, the magnitude of your vector, which is going to be written as r, to be written as r raised to power 2 is equal to ab raised to power 2 plus bc raised to power 2, and you can all rewrite this one as r is equal to the root of ab raised to power 2 plus bc raised to power 2. So just pardon my writing and try as much as possible to follow along as I'm writing this thing, because the screen is pretty small and my thumb is pretty big. So this is what you can write your magnitude as. All right, so the vector sum is given by a single equivalent vector joining the beginning of the first vector with the end of the last vector. This is what I was trying to explain to you in the earlier sum of vector. If you look at this one now, you have a plus b plus b plus c plus c plus d. You can see that what they are joining is that they are joining this single equivalent vector a with the single equivalent vector e to give you ae as the sum. So, and then the vector diagram is closed, and then the end of the last vector is joined to meet with the beginning, as per according to the diagram that I drew for you earlier. So this question says the coordinate of the center and the radius of the circle y raised to power 2 the coordinate of the center and radius of the circle y raised to power 2 plus x raised to power 2 minus 14x minus 6y plus 56 is equal to 0. Okay, though I've like written out the steps here, I've like typed it out, so I'll still try to like try and calculate follow along and see how it will just try as much as possible to be able to grab a point or two. Now, what this question is trying to tell us is they are expecting us to express this as a particular formula, as a particular equation, which is the equation of the circle. So let me start by cleaning up my space here. So looking at the equation that we are given y raised to power 2 plus x raised to power 2 minus 14x minus 8y plus 56 is equal to 0. Okay, let's try and group and collect, like, categorize it according to like the like terms, because that's what I did first. I first of all categorize it based on the exponents, which, like, okay, well, let me group all the exponents together, and then I now categorize it based on the like terms. I put all x together, all y together, then putting the whole number to the right hand side, which is where the zero is situated. So this is written like this. This thing is going to be messy. X raised to power 2. Oh, sorry, this is minus. Let me try and read this thing. I'll just work out the necessary steps that I missed in this explanation. So you have x raised to power 2 plus y raised to power 2 minus 14x minus 8y is equal to minus 56. So like I said, the very first thing is to like group all the x together. So this is me bringing x raised to power 2 and 14x together, because both of them, they are like x with different coefficients. So now this is y raised to power 2 also like grouped with minus 8y. Both of them, they have the y variable. Now bringing my plus 56 to the right hand side gives me minus 56. So now what I did here, I said applying completely the square method to the equation. So the reason why I am applying completely the square method to this situation is because looking at this, okay, first and foremost, it is polynomial, but the type of polynomial that it is that is just a quadratic equation, because the highest exponent here is having an exponent of 2, so it is quadratic. So, and completing the square method is one of the methods of dealing with quadratic equation. So this means our x minus x raised to power 2 minus 14x is going to be one unit of a quadratic equation, while y raised to power 2 minus 8y is going to be another unit of the quadratic equation. So, and then with completing the square, I can just add my b over 2 raised to power 2 to both sides. So that means the coefficient of this particular x over 2 raised to power 2, all raised to power 2, then the coefficient of this one over 2, all raised to power 2, I'm going to add it to both sides. So what that place is doing is just doing x raised to power 2 minus 14x. So for completing the square, my b over 2 raised to power 2 is going to be plus, open bracket, 14 over 2, close bracket, all raised to power 2. Then in continuation, it's just that single line cannot contain everything. So then we have a plus y raised to power 2. Then we have minus 8y. So then my b over 2 raised to power 2 here is going to be plus 8 over 2, all raised to power 2 again. Then is equal to minus 56. I said I'm adding it to both sides. So this is going to be plus, open bracket, 14 over 2, all raised to power 2, then all raised to power 2, then plus, again, open bracket, 8 over 2, all raised to power 2. You guys should like try and understand this a little bit. All raised to power 2, sure. So if you look at this thing now, we have our 14 over 2, we have our 8 over 2. 2 here will give you 1, 2 here will give you 7. 2 here will give you 1, 2 here will give you 4. So the same thing goes for this place and this place, this place and this place. So this whole expression becomes 7 raised to power 2. This whole expression becomes 4 raised to power 2. This one becomes 7 over raised to power 2. This one becomes 4 raised to power 2. So if I clean this up now, the result of this particular expression is going to give me x raised to power 2 56 plus 7 raised to power 2 plus 4 raised to power 2. Right, so that's going to give me the answer. So by the time you look at our 7 raised to power 2, it gives us this 49. If you look at our 4 raised to power 2, we look at our 4 raised to power 2, it gives us this 16 here. So that's why I have the x raised to power 2 minus 14x plus 49 plus y raised to power 2 minus 8y plus 16. So for this right hand side, it's actually cool and okay to like expand it. But for this left hand side, leaving it as 7 raised to power 2 will actually make it easy to segregate and bracket it and like collect like times for you to find the common multiples there. So what you do here is for you to do this is x raised to power x minus 7 raised to power 2. Yeah. So we have, let me clean this space off. So what happened here is these are 49. By the time you take all of this together, this one will give you x raised to power 2 minus 14x plus 7 raised to power 2. So when you look at your x raised to power 2 and 7 raised to power 2, they are something, it is something you can group together. So when you group that one together, you have x minus 7 raised to power 2. And if you open your bracket, you are going to get x raised to power 2 plus minus 14x plus 49. So this is like two things that you can multiply together that will give you plus 49, and you will add them together that will give you minus 14. So it's actually like plus 7 and minus 7, something like that. So doing that one is where we have our x minus 7 raised to power 2. Then for our y raised to power 2 minus 8y plus 16, this is just looking at two things that we can multiply together that will give us 16, and like we'll add them together and it will give us minus 8, kind of like that. So but leaving this as 4 raised to power 2 will make it easy to evaluate and come down to this bracket. So now our 7 raised to power 2 we evaluate it as 49, our 4 raised to power 2 evaluate it as 16, and by the time we add all these three together we get 9, and our 9 can also be simplified to be 3 raised to power 2. So if you look at this particular form here, x minus 7 raised to power 2 plus y minus 4 raised to power 2 is equal to 3 raised to power 2. It is the same thing as x minus h raised to power 2 plus y minus k raised to power 2 is equal to r raised to power 2. So now we've expressed the equation that was given to us as a form of this particular equation of the circle, where we have our x to still be our x, our h to be 7, our y to be y, our k is now 4, where and our r is 3. So that's the expression. So the center of the circle here is we have our height is 7 and our k is 4 and the radius is 3. So that's it. The coordinate are 7, 4, while the radius of the circle is 3. Alright, that's that about that question. The gradient of a line, when we say the gradient of a line is defined as the ratio of the vertical distance the line rises or falls to the ratio of the horizontal distance. The equation of a line is actually y is equal to mx plus c, where we have our y to be the coordinate on the y-axis, our m to be the gradient, our x to be the coordinate on the x-axis, and our c to be the intercept. But nevertheless, as this line is as this particular definition says, our gradient m is actually equal to dy over dx. So the y is your y-axis is your what's it called, your vertical axis like this, while the x-axis is your horizontal axis like this. So the ratio, the gradient is the ratio of change on the y-axis to the ratio of change on the horizontal axis. So you can have your m written as Okay, you can have your m written as y2 minus y1 over x2 minus x1. That's our what's it called? That's our m for us, our gradient. Now this next question says if A is 36 and B is 48, find the coordinates of the midpoint A, B. Okay, the very first thing you need to know here is the formula for the midpoint of a particular line segment. You are looking for the midpoint. Midpoint is half, right? So we are looking for the average of the segment of line A and the average of the segment of line B. This gives us the formula 1 over 2 of x1 plus x2 and 1 over 2 of y1 plus y2. So if you sum this, if you evaluate that one, it's going to give you x1 plus x2 over 2 and y1 plus y2 over 2 as the coordinate of the midpoint of 2 points on Cartesian coordinates. So when you look at the given coordinates, we have they said A is 36, A is equal to 36, and we have our B is equal to 4. Apologies for the quick for the small break into transmission. I just went to check angle of slope and what's it called that was written inside the material. So angle of slope is said to be tan theta, which is equal to sin theta over cos theta. So here I have my tan theta, and where my theta is, I have my I have my what did I even do here? The arctan of the slope. Guys, hold on. Let me quickly check my calculator if I'm correct on this one. I'm not even sure if I have arctan here. Okay, I have arctan. Arctan of my slope. My slope is 1. Alright. It's 45 degree. Actually, the formula for this one is actually theta is equal to the arctan of m. Theta is equal to the arctan of m. So you have your angle of slope is written as theta is equal to tan raised to power minus 1 of I think I can write this. I can still write this better. Theta is equal to arctan minus 1 of n. So our theta is the arctan of m. So and from what we calculated, our m was 1. So that means our theta here, which is the angle of the slope, is going to be the arctan of 1. So which gives us our 45 degree that I just confirmed from the calculator. So that's for the angle of inclination there. Now this next question says if A is 3i plus 4j plus 5k and B is equal to 2i plus j plus 7k, find A dot B. Now when you see anything dot actually signifies the product, like multiplication of two things in your vector. So now when you have A dot B, A dot B. What you do is you take each individual unit vector, you take their coefficient and you multiply it together. So considering the what's it called, the arithmetic operation between them, whether it is positive, is plus or minus, you have to consider that also. So our A dot B is taking our A1 times B1 plus our A2 times B2 plus our A3 times B3. So by so doing, we are taking each of these values, taking out their coefficients and multiplying it together. So in simpler terms, what we just did here is okay. What we just did here is so we have 3i. We also have 4j plus 4j. We now have plus 5k 5k. So we now have the second line that we have is we said B is 2i plus j particular units.